Peter Cha is up next.
Hi, everyone. My name is Peter Cha. And today I'll be talking about, I'll be introducing a new method for tomography based on a machine learning approach. And so first I thought I'd start by introducing what tomography is, what tomography in a quantum state is. And so over here you have a quantum computer, an example of a quantum computer that is operated by IBM. And actually it's kind of cool that quantum computers similar to this one are actually available for public use, free of charge. And we use a quantum computer similar to this one to generate the data that we use in this talk. And so the way a quantum computer scientist might use a computer like this is to set up a circuit which consists of a series of operations that are carried out on some NQ number of qubits. But of course, real quantum computers, is there time or anything? No, there's no clock.
I can give you a warning.
Sure.
Yeah.
Yeah. So, of course, real quantum computers will not realize idealized states, and so real quantum computers will realize this plus some noise. And so this noise might consist of errors in initialization. It might consist of errors in the gates. It might consist of measurement errors. It might consist of decoherence over time. All of those things like that. And so what really happens in a real quantum system is that the quantum computer will actually be described by a density matrix, which is the intended state plus the noise. And so how do we know what density matrix is really being constructed by the quantum computer? So we proceed by making a series of measurements, a series of projective measurements by preparing the quantum state quantum computer in the same way many times, and taking a projective measurement for each realization. And so on the right you have a series of measurements that you might get out of a quantum computer like this. Then tomography is a task of reconstructing the density matrix that accurately describes the real quantum computer based on the measurements that have come out of it. So this is a difficult problem. Tomography is a difficult problem because of something called the curse of dimensionality, which is the statement that an n-qubit system is described by a density matrix which has on the order of 4 to the n-cube complex parameters. And so this exponential scaling really makes the task of tomography difficult. And so just to give an idea of what this scales like, for 10 qubits, this corresponds to about 1 million parameters, which takes about a megabyte of storage, which is reasonable. For 20 qubits, we're talking about a terabyte of storage, which is already sort of stretching the amount of storage that we're able to handle, and is pretty much beyond what we're really able to work with on a real life basis. And just as a way of comparison, the total amount of information that is available in the Library of Congress comes out to about 20 terabytes of information. And so earlier this year, there is a quantum computer that was constructed by Google with which they declared quantum supremacy. And that quantum computer had 53 qubits, which corresponds to 10 to the 30 parameters, which takes 1 quintillion terabytes just to store, forget working with. Yes?
So presumably, you have to do a lot of bit sequences to characterize that density matrix too.
Yes, I mean, right. So
it's not just storing the density matrix.
Yeah, so here I'm just talking about like the most general possible density matrix. I'm not thinking about like specific states that are realizing. And so because of tasks like this, reconstructing so tomographic methods have traditionally been restricted to small system sizes. And so a common method that is used currently is something called maximum likelihood estimation. And this method is really restricted to fewer than 8 qubits. And so what we would like to do, the real the gold standard thing that we would like to do is carry out tomography with data and processing time that is polynomial in the number of qubits rather than exponential. And so recently there was progress made in this area by introducing the idea of generative models to tomography. And so this was first done by introducing restricted Boltzmann machines by the group of Roger Melko and Giacomo Torlai. But even these were restricted, and they continue to be restricted to pure positive states with restricted system size. Success in scalability in going to larger system sizes was demonstrated by using recurrent neural networks by one of our collaborators actually, Juan Carrasquilla. But recurrent neural networks are inherently designed for short-range correlations and are not well suited to the kinds of long-range correlations that you might expect in quantum systems. And so in this work, our focus will be the attention-based transformer, which is a state-of-the-art natural language processing architecture. And as the talk goes on, I'll describe how this transformer works and why we expect it to be well suited for our problem. So the transformer network in the natural language processing field has been demonstrated to be efficient in training and post-processing. And so in the work where it was originally proposed, it was able to learn English using 2.2 million sentences, which can be contrasted with something like 10 to the 107 total number of word combinations that are available in the language. So which is to say that the transformer is able to learn languages efficiently with a sample size that is much, much smaller than the total number of available sample sizes. In addition, sampling from this model, so this is a generator model, which means the ultimate task is to be able to generate samples from it. So sample is linear in the length of the sentences that we're interested in. And so this is originally applied to a translation task. So I'll sort of give a quick demonstration of what it looks like in translation. And so suppose we wanted to translate the sentence, the animal didn't cross the street because it was too tired. And so the way the transformer would go about this is it would look at the sentence, then given this English sentence, it would start translating to, say, French. And it would do this by generating the first word, which I will not attempt to pronounce because I don't speak French. And so given the English sentence and the first French word, it will then generate the second word, and then the third word, and then the fourth word, and so on and so forth. And so this is what I mean when I say that the sampling is linear in length, as opposed to taking the English sentence and then scanning the entire range of all possible French sentences to pick the right one, which requires an exponential number of sampling, exponential sampling time, and is difficult. It's not practical, rather. So how does it actually work? So the important keyword here is it. We want to focus on that for a minute because this it is ambiguous and translating it is a difficult task. And because depending on whether the word it is referring to the animal or the street, it can be translated in different ways in French. And so the transformer accomplishes this by first connecting this word, realizing that it has a correlation to the word tired, then based on these correlation, realizing that the word has a correlation to the word animal. And then based on these conclusions, the transformer is able to determine that the correct translation of the word is this other word that you see over here. And so the actual architecture of the translator consists of two separate parts, the encoder and the decoder part. So in each, the transformer starts with the language, then studies the self-correlations that are present within it, for example, by comparing the different words and studying what correlations are available. And then based on what it has learned about each language individually, it is then able to study the correlation across languages, after which it is able to generate the sentence correctly. So for the purposes of our model, we will be using just the decoder part. And the reason for that is that the encoding is really done by our quantum computer. So the quantum system takes our intended state and encodes the correlations in the POV measurements. Our decoder can then study the self-correlations that are present within the POV measurements, after which you can generate the information and then move on to the step where we generate the density matrix. So first we'll benchmark the transformer. And so we'll be studying the GHC state, which has a state that looks like this. And we'll measure our accuracy of construction by the classical fidelity. And so this is a number that goes to 0 if the two states are completely different, and 1 if the states are completely equal. And we'll be plotting the minimum number of samples necessary in order to achieve a certain classical fidelity and comparing the result of the RNN versus the transformer. And so in the RNN, you can see the sort of very nice results that the NS scales linearly with the number of qubits. Number of qubits here. And the transformer achieves the same linear scaling in the number of samples necessary to achieve the classical fidelity, except with an order of 10 reduction in the number of data that's needed. 2 minutes? So now that we've established how the transformer compares to other generative models, we can now proceed to territory where no generative model has gone before, which is to reconstruct the actual density matrix of a real quantum computer using the IBM computer. And so for a GHC state, we expect the density matrix that looks like this, where there's 0.5 in all corners and 0 everywhere else. This is the density matrix visualized using the maximum likelihood estimation method provided by IBM. And so here we would expect to see 0.5 on all four corners for an ideal GHD state. But of course, this is a real GHD. This is a realized quantum computer, and so we can see that there's error on each of the bars on the order of about 10-20%, which gives an estimation of the accuracy of the IBM free quantum computers. And we can compare that with the density matrix output by the transformer, which looks nearly identical up to some measurement nodes. We can also use the transformer to detect faulty qubits. Yes?
Was your goal to do a better job, or was the goal to duplicate the IBM one because yours is so much faster?
We begin by duplicating, and then so maximum likelihood estimation is limited by system size. It works really, really well at small systems and does not work in larger systems.
And your method is scalable.
Yes, our method is scalable.
Well.
Exactly. Good. And so the next question that we like to answer is, can the transformer detect a faulty qubit? And so in order to do this, we introduce a very simple error model where a single qubit has a probability of being flipped between 0 and 1 with some probability p. And we'll measure the accuracy of reconstruction by using this exact quantum fidelity, which we're able to calculate because of our small system size. And we'll find that the fidelity should be like 1 minus p. And so that we should be able to read off p just by looking at the reconstructed quantum fidelity. And so this is the result that we see from the transformer. And so with increasing p, you can see that not only does the quantum fidelity decrease linearly with p, but it also is a good estimation for p itself by using this formula 1 minus p here. So future directions. So there are many questions that remain. This is a promising method that has been proposed, but really the bulk of the promise remains to be seen. And so the one question is classical fidelity a good measure of reconstruction quality? And another question might be, how does the results, the linear scaling in the number of samples needed, change when we consider more complex state beyond the GHD state? We might also, of course, want to eventually carry out density matrix reconstruction on a larger number of qubits, as well as incorporate maybe more complex error and noise models that might be more realistic towards what are seen in quantum systems. So thank you for your attention, and I'll be happy to take any questions.
Did I understand that you could tell IBM that one of their qubits was faulty?
We would be able to, yeah. We are able to.
You haven't done that yet.
I mean, all of their qubits have some error rates, and they carry out like benchmarking on a daily basis. I think they're sort of like benchmarking, and then like state repreparation like happens like once a day or once every 3 days.
I see.
So it's definitely something they're aware of, but they don't publicize because they don't like having an error rate of like 20% for 3 qubits really makes it difficult to do large numbers of system sizes, and so it's not really something you publicize. But
well, I'm just wondering whether you communicated with them today. The qubit number 7 seems to be lagging.
we did not.
I think they'd appreciate.
Yeah.
We've got a tool that can do this easily. That's.
You're right. We were, yeah. It is cool.
It is an actual computer. It's not one of those simulated.
No.
They have classical computers that pretend they're quantum.
They do. Yeah. No, it is a real life, genuine quantum computer. I was surprised by that too.
Yeah. Okay. Free.
Free. Yeah.
For you.
It's restricted. No, for everybody actually.
Yeah. I mean, yeah, not to build, but.
Yeah. Yeah. But it's like restricted. It's like you can use like maximum 15 qubits or something like that.
You can like pay to unlock more or something.
I'm not sure. Probably.
Thanks.